Okay, we continue with the presentation of the results or summary of the breakout sessions. So some of the breakout session leaders are still sending their stuff, so we will just do it while they come in and while they send the stuff, so it's been improvised, but we'll manage. So we start with the sensing metrology session that was in this room here.
Okay, we had a very long and detailed discussion about the first topic here, about the top-down versus bottom-up approach. What does that mean? The discussion was about where should the innovation come from? Should it come from the scientists? Should they propose applications and pose ideas on what we could do with quantum technology, or should the users define use cases, and then everybody, not only quantum technology, can contribute their expertise in solving a specific problem. That was in part initiated by the new information about the missions, that the future program might be structured into missions, which honestly was new to us as well as of this morning. So that was what the majority of the discussion was actually about: how to structure this process and how to define projects that would generate the most impact in the economy.
Yeah, and a very interesting topic that was mentioned during the discussion is really how can we find applications. So I'd say that in most cases, quantum technologies are still looking for applications. You know, we're really in the same situation that the laser was in the 60s, and this is maybe something that we can improve in order to develop the connectivity between quantum scientists and the market. So try to make scientists aware that there's something really important outside the quantum world. Try to keep them aware of the market needs, of the industrial constraints, and maybe one way to educate our community is to set up workshops and online platforms in order to improve the discussion and make the connection and the dialogue better between all these communities so that we understand each other better.
Yeah, we thought that we should establish certain communication platforms and organize workshops to bring industry, users, and the scientists together to define these application scenarios. That was one of the major outcomes, I guess. Yeah? What we did not manage to achieve is to actually discuss the content of the possible new version of the strategic research agenda, which platforms we should support most. I think that would have to be continued offline or during the workshops or during other communication channels.
We completely realize that what's necessary is a very difficult exercise. If we want to build an industrial roadmap, what would be ideally required is that we have the capability to cross all available technologies versus all potentially addressable applications. And also this cross analysis needs also to take into account the business case to see what kind of economic impact, what kind of revenues we can expect from a quantum disruption. So there were still discussions regarding the level of details that we need to include into the strategic research agenda. How can we include this business case analysis? Do we need to do this for cold atoms, NV centers, electrometers, magnetometers, atomic clocks? Well, there's a very broad scope of technology that we can propose. This technology can also address a very broad scope of application, and turns out to be extremely difficult to end up with a very refined analysis that will allow us to define priorities and define very clear objectives. So we haven't come to the stage where we can make conclusions and propose very clear directions in our research activities, but that's certainly something that we need to work on in the coming months.
I think that's a specialty of the quantum sensing and metrology platform in contrast to the other platforms. It's very diverse, it's very different applications, different requirements, and therefore it will be very difficult to down select to just 2 or 3 projects in the end, or directions that the community may want to go. Another point that actually came up was that although one of the key features of quantum 2.0, if you like the term, is entanglement, of course. Yeah? But I think within the people that were assembled, we all agreed that we would want to use entanglement only if it actually helps the application. If not, yeah, we rely on classical spin systems or the excellent controllability that we have with cold atoms or NV centers and so forth, and just not do entanglement if it's not required for an application. Well, if it comes for free, I guess.
Oh, well, maybe the discussion. No, but just okay, one second. Just to give a clear example, the way it's written in the strategic research agenda today is that we start with superposition and then we add entanglement to improve the products. Well, I don't think we should to be that dogmatic. We need to do it only if it makes sense from an applicative point of view.
When you say entanglement, you mean entanglement / squeeze?
Yes.
Yeah. Squeezing is entanglement.
All right, so I think we have to stop here. Thank you very much.
Thanks. So we will continue with another application area. So let's continue with Jens. How about that? So this is, as I said, a bit improvised, but we will just...
Very good. Let's see. Okay, very good. Okay. Well, welcome. So let's move to quantum simulation. That, in contrast to fully fledged quantum computation, is in the unlikely event. We not only need quantum technology, we also need classical presentation. Okay, that's good enough. Very good. Okay, so quantum simulation, in contrast to full Monty quantum computation, is kind of special purpose. It's also teleologically more problem-driven, aimed at understanding properties in one way or the other, with industrial applications being of the type of like maybe companies offering cloud services in one way or the other. Now, quantum simulation basically comes in three flavors: chocolate, strawberry, and in analog quantum simulation to start with. That's a setting where you would have a system prepared and let it just go under its own Hamiltonian under very precisely controlled lab conditions. So in order to arrange for our kind of goals or to contribute to a kind of roadmap, we built upon our earlier roadmap that collected input from the entire community over the years in a painful exercise. So we are basically building upon that now in our discussion. So the short-term goals here would be more like condensed matter driven, of simulating strongly correlated matter in the way it lives up to this term. Think of improved control, better temperatures, really kind of better getting a handle on the platform, experimental platform at hand as a short-term goal. Longer term, there's lots of exciting condensed matter problems to access, and going high energy to go into the realm of simulating high energy problems on the analog computing side. Digital computing is different. You kind of snapshot your dynamics or your properties in a kind of gate array fashion. This is not so much aimed at quantum condensed matter, but quantum chemistry and material science. And we hear about a number of how much of the supercomputing power of modern computers is aimed at understanding materials in one way or the other. You would be surprised to hear that number. So here, it's in the short term about digital interactive, like loopy type hybrid methods bringing together classical and quantum algorithms to solve quantum chemistry problem without fully fledged, without any quantum error correction whatsoever. Showing a quantum advantage as a milestone of outperforming classical supercomputers no matter what is surely on the way and on the radar for the next, months, years, days to come. In the medium, longer term, small-scale quantum error correction or intermediate approximate quantum error correction will have to be on our mind map and presumably also on the experimental map. The third flavor is quantum heuristics, or we just coined the term. That's everything in the middle, and for industrial applications, that might be the maybe most interesting focal point. So here, it's about improving annealers, like coherent or quantum-enhanced annealers of some kind. There's also lots of theory work to be done of what this is about. Thinking of more industry-motivated applications. That's a homework to both experimentalists and theorists alike on routing, portfolio optimization, pathfinding, like industry-oriented special-purpose problems run on special-purpose quantum devices in a way. That's kind of short-term. Longer-term is to think of quantum-enhanced machine learning, like quantum machine learning with classical tools, quantum machine learning for classical system, classical machine learning for quantum system, or really showing the full potential of machine learning in the quantum world. That's all I wanted to say, except the number that's still missing.
I would just add one thing. One thing that came up in the discussion, and I guess maybe can be picked up later or maybe not, but this digital quantum simulation is of course very similar, or will develop into this direction of quantum computing. And I guess the question is a little bit where the boundary is. We found a little, or let's say the feeling was that without quantum error correction, it fits into the quantum simulation part, but I guess that is determined. Or maybe there should be no strict boundary anyway. Yeah. But of course, simulating these type of problems is an important part for both parts. And with the digital part, you of course go closer to problems that are actually industry relevant. And yeah, a large part of high performance computing is already used on materials, of course, in more the classical regime. And therefore, this could be a quite interesting topic also to connect to industry.
What is the difference between coherent quantum annealers and analog quantum simulation? Or another way, couldn't you fit coherent quantum meaning in simulation?
Well, I would argue, that's that all that is simulation in the several flavors.
So why do you need a special thing?
Well, I think, that's why you can see the kind of the nice blue circle in the background that hints this. So my answer is look at the design specifics, because it's very much that right. If you want to ask for a kind of a borderline, the analog computation is really having all your knobs at hand, and then you do something like cool as much as you can, then you go for it and have a fixed set system going under its own Hamiltonian, and then you pop that. That would be the core idea of an analog simulator, whereas of course in annealing you would have time-dependent paths, you have more time-dependent knobs. It's on that sense more sophisticated, but less so because you have like easing tight Hamiltonians and not like very strangely topologically ordered whatnot Hamiltonians on the other side. That's the separation. But a fair answer would probably outrun our 5 minutes. Thanks.
Maybe it makes sense after simulation continue with computing. Ferdinand and Walter, are they here? If not, then we go to communication.
Okay, maybe while the computer is set up, I have some good news about Rob Hugh. I talked to him a few minutes ago, and he should be coming in anytime, certainly before lunch. So if he is standing in front of you or just behind you in the queue, please let him have a seat and bring him some food he needs to eat.
Thank you very much. So we had a very interesting session in the communications area, and we were also joined by Martino from the JRC, who gave us some input from their recent documents as well. So we posed lots of interesting questions. We focused mainly upon what's written in the SRA at the minute and how we can improve upon that. The SRA is already quite detailed, actually, but yeah, we were thinking about how we can improve it. We also asked some more general discussion points about things like why aren't more people buying this technology? How can we better integrate with other communities, such as the classical cryptography community, for instance? And how do we better explain our strengths to the communities at large? But we didn't have time to discuss all of those points, I must say. So here we have a short summary of the various points that we did discuss. So we had quite a long discussion about the 10-year vision for the communication area, and especially the vision for entanglement-based networks. Do you want to say something about that, Nicola, so I don't steal?
Okay, so indeed we had some discussions there, and there were essentially people who were saying, okay, we should have a very broad vision for a universal quantum communication network, a bit in the spirit of universal quantum computing, and be open also to possible future discovery and new applications. So that is certainly one important vision to maintain and develop. And on the other side, there were also people saying we are too vague and we should be more precise. And I think that's not incompatible. We can have this vision and we should have it. But at the same time, there is also a need for specific target, both for just, let's say, trusted node-based systems, but also for entanglement-based metro area networks and connecting cities. So then we should also have applications for these quantum internets beyond encryption. So once you have a cryptographic key, you can of course use it for encryption, as we all know, but you can also use it for digital signature, for Byzantine agreement, for some multi-party computation. And maybe we should here be more precise what we can do with that and what we cannot do, what require more elaborated quantum communication networks. Also about scalability, in the present document, we always talk about 1,000 kilometers. It's a nice target. We should maintain and reach that, but we should not stick to a one-dimensional scalability target, but also go to 2 dimensions. We want a real network that goes really in the 2 dimensions and maybe 3 dimensions, but let's stick with 2 dimensions for the time being.
Okay, so I think the SRA naturally concentrated on the 3-year targets, but maybe this is the time to now better elaborate 6-year and 10-year targets as well. So then a second area that we discussed in some detail was about the proposed quantum communication infrastructure. Some people asked, do we really need a quantum communication infrastructure? Are we going to learn anything new from building such an infrastructure? But then we also heard the other side of the debate, that we will learn lots of things, and actually it'll help with defining standards, a certification process, and for developing applications. So end users can use that infrastructure for building various applications on top of the infrastructure. And there was an analogy made with building a transport infrastructure. So, you know, we wouldn't be able to, we wouldn't have the transport infrastructure that we have today if somebody didn't make the decision to build the roads that the cars will operate on today, or to build the railroads that trains run on today. So it can have a positive impact upon the development of applications in this area. Anything you'd like to add to that?
Yeah, maybe I don't know if it comes afterwards, but certainly once we have this backbone, this quantum backbone, the access to this quantum backbone will involve probably a bit of quantum access, but also a lot of post-quantum cryptography to access it. So there will certainly be a mix of post-quantum and QKD-like.
Okay, and actually that touches on the next point that we discussed in some detail as well, about the importance to attract expertise which is outside of our current community, the quantum community, in particular engineers, telecom engineers, and crypto people. Would you like to say a bit more about that? Okay.
Okay, well, I'm essentially reading now, so focusing on building prototypes and complete systems. I guess, again, you see we still have prototypes to build and new things to develop, but there are also complete systems that are not at the same TRL level. And, okay, that was what I was saying before, these hybrid quantum and post-quantum safe solutions, for instance, to access this quantum backbone. There are also some elements in the supply chain which is completely missing in Europe, like the semiconductor single photon detectors. You can buy them in the US, from South Korea, in China they make it, but we have nothing in Europe. That's also probably a problem that goes beyond just the flagship, because it's a huge project in itself. Requires very specific know-how. Yeah, and here again, having a quantum communication infrastructure will help, because that will provide an initial market for this supply chain.
Okay, and then the final point was we discussed that we should explain the advantages of quantum communications and quantum cryptography specifically more clearly. Explain what the threats are. Some of the people in the audience actually didn't understand what the threats are. And I think the fact that the EU are going to announce that people should move towards quantum safe solutions in the future will be very helpful for us, and perhaps potential customers will understand those threats a bit better. Also, we should explain that really the killer application at the minute is for long-term sequencing of data. So cryptography that's based on computational complexity, of course, can always be threatened by improvements in technology and new mathematical techniques in the future. So that's really the advantage that we can offer in quantum cryptography, and we have to explain that advantage more clearly. So that's about it. We didn't cover everything, I'm afraid, but we discussed some interesting things for sure.
Okay, so we have quantum computing next.
Okay. Yeah. Okay, so
good morning still. So we really had a discussion on, my name is Walter Ries, I'm from IBM Research Zurich, and together with Ferdinand Spielkaller and a very, let's say, a very good team who was very active and gave a lot of input, and we had very lively discussion, and we discussed on quantum technologies and in particular quantum computing, and we phrased it intentionally quo vadis. And the starting point of our discussion was a very simple one, and this is to put the investment of the flagship also in some perspective of what's going on elsewhere. And elsewhere means we are talking about, of course, about China, and we are talking about the US government. And these are actually the US government, the latest numbers are 200 million, but if you talk about the 200 million per year, this is typically on very strategic programs. And in addition to that, this number does not include, and this is a hidden number, what is spent on a military base. In addition to that, we have the investments of China, and China invests 10 billion actually in a single site, mainly focusing on communication. And interestingly, this type of major players, they clearly have a master plan. They clearly have a strategic master plan on developing specific roadmaps. So this is actually how we have to put this investment in different areas. Like to
where this was also confirmed by the discussion, where members of the audience would highlight that there's private money going in and a lot of additional money going in on top of the numbers which are given here. In the two cases of US and China.
So this is what we just mentioned. So China focused, US is focused, and of course we also realized how can you be focused? How can you be, let's say, make strategic decisions? If you make strategic decisions on a technology, you have to have a metric, and the metric has to be, let's say, mimicking the technology, it has to mimic the weakness and the strengths of the individual technologies. And I think something which is very important, it is also important in the future, and this is for the second phase also of the flagship, we need to come up with a metric which allows to compare the different type of technologies, because it is important. You can have a very good engine in a car, but if your wheels are weak, you will never drive fast. This is you have to understand. This is the meaning of the So we ask a very simple question, and the very simple question is,
or do we play a leading role in this endeavor? Okay. That's broken down into a couple of smaller questions which we asked which we asked the audience, and actually, are we at the stage where networks can focus on one scientific goal? This would have the benefit that it allows joining different platforms, all going for these different goals, so semiconductors or superconducting qubits, and you can basically join them under a common goal. But even that is not clear whether we have one common goal of quantum computing. The other option is to go more along technology goals and to have a close integration of science and industry partners. And in the discussion, we had a couple of comments, and for example, optimization in future flagship calls could be still done because, as it was mentioned, this was still along the old style of projects, but we have answered that this is just the wrap-up phase, and it just shows the initial phase of this flagship, so obviously there can be some optimization in the calls.
But there was also a general consensus that the quantum flagship, how it was, let's say, driven and how it was established, and really was appreciated, that it was really the attempt of a new approach, also bottom up, and I think it was highly appreciated that this was not only a top-down approach, and really it goes also, a lot of credit also goes to Tommaso and the teams here who really makes this happen, so this is very good. What was also specific, and this also was put into the bigger context of, let's say, focus and converging to different or to a few technologies. And in that respect, it was also very, very clear that if you focus, you really have an understanding on the system view. You really have to understand. You really understand if you focus what you try to optimize, and this means the system view really has to be taken into account right from the beginning. And this is at a stage where I think none of the existing platforms are there yet. This is at least our opinion.
But the opinion was still to scale up along the roadmap some of this and test the scaling up basically, while at the side having some boiling ideas and feed this whole evolution by new ideas which are coming from the side. So it was kind of this two strategy going along with the existing and kind of a little bit more mature technologies, while still keeping the competition still open, because it's not clear actually, and we have had this opinion in the panel also in the discussion round that it is not yet decided what are the leading technologies. Even though industry is kind of putting a lot of money into one, this does not necessarily mean that this is the leading technology.
But the important point is also, if you have a super wild duck idea, you have to ask the same technology questions. You have to ask the same technical questions whether your super wild duck idea fulfills this. So So how to attract key European industry players. So in principle, first of all, we have to divide this question in principle into two types of players. Who are the major IT players in Europe and who are driving this IT roadmap on a European side? And then you can look around and then you suddenly realize that the European landscape, particularly of European IT manufacturer, is in principle, it's empty. And this is something which is a piece which is missing. A piece which is missing, and if you would like to lead in IT for the future, and those of you who attended Heike Wiel's talk, and she mentioned that quantum computing is one part of the IT roadmap in the future. So this is a strategic part where Europe has to think about. And then the other part, these are the users, and the users, this is, in that respect for the users, there is, some of them are experienced, some of them have made already investments, but some of them are really newcomers, and the newcomers also need to be trained and educated, and even those who are experienced, they have experienced that they have to invest a lot in order to formulate their problems, which to be then tackled with a quantum computer, a future quantum computer, and then to define a roadmap where this quantum computer might even impact their businesses. And I think this is very tricky. And here you have, and this was also a consensus, you have to start now thinking about this because time is ticking. And for example, I make an artificial case. If in 3 years, whoever has made a breakthrough in quantum computing and suddenly you realize that you can scale it up and the technology might be ready in a few years, I think most of the companies would not be ready because they do not have the people who are skilled in this new type of technology and can apply it immediately. And if they would like to become ready, they are now challenged because they are in competition with their competitors and the market is empty. So we have to tackle this problem from two aspects. We have to educate the potential users, but we also have to build up the ecosystem, and this is part where academia is a task.
So to me also an important point was that it was brought forward that European role could be also, or some role in Europe could be to provide software engineering for future quantum hardware coming from China or US. Well, I put a question mark because I would be unhappy with a solution which is limited to this and that we really restrict ourselves to suppliers of foreign technology.
I think we have to speed up a bit. Okay.
Almost. Pick the two most important ones. 1.5. Okay,
so very simple. We had this simple question: big localized centers and/or distributed networks of excellence. There was a clear consensus that we should have distributed centers of excellence within Europe of different velocities and also with different industries distributed in different countries. And then the most important chart we have to do. This is something, these are the industry players, how to build a self-sustaining industrial academic ecosystem. Of course, we forgot something. These were the government and research labs. And we think that such type of ecosystem, the ecosystem is now here. Of course, we did not finish because otherwise we would even be later. So we think the most important thing is what needs to be provided. This is quantum computing resources. Quantum computing resources, these are building the nucleus of an ecosystem for academia, which then further develops these resources, and where you can integrate major industry players, small and medium enterprises, early adopters, and even a startup society. Of course, we have to rework this picture. The arrows are a bit wrong, and we apologize for running over time. Thank you very much. Thank you.
So we'll continue with basic science, Anna and Tillmann. And we are, as you have noticed, running quite late, so may I ask you to stick with the 4 minutes
audience. Right?
Yes.
We just have one slide, so right?
Yes.
It will be short. We had a lively discussion about basic science.
We could do it with 0 slide.
Should we do it? You want to start?
And we may try dancing. You want some magic trick? Look, it works.
Works.
Okay, you want I start? Yes. Well, basic science, of course, has a particular situation. But for young people who do not know the evolution of Europe support to basic science in the last decades, you should know that until the 4th framework program, the Commission was supporting basic science. And then at one moment, they decided they would no longer support basic science, saying that it was the role of nations, okay, to support basic science. So there was a lot of protest in particular from science academies in Europe, and this led to the creation of the ERC, European Research Council, okay? And so it's very good that now in this context, again, we are allowed to use the word basic science for a program support by EU. So this really very good. Now, when it comes to this flagship, I think we have to put our arguments in the context of the flagship. In the flagship, we have to say that quantum technologies are certainly not mature, and they need a lot of basic science, okay? And what we want in particular to stress is basic science efforts, which will be more efficient at the EU level, which means that it demands collaboration, networks, etc. And so just to give a few examples, because of course in basic science, freedom is really the basic notion. Anyway, I must say the audience was extremely reactive, made plenty of proposals, and we tried to make a small synthesis of the proposal. So I start and you continue. So robustness, yes, robustness of quantum processing, which in a sense is linked to the idea of decoherence-free, protected subspaces, etc., etc. Exotic materials, I mean, people say, I don't know anything about that, but some people told us that they are really working on materials which could play a fundamental role in quantum science. The idea that the concepts of classical information are useful when you try to apply them to quantum information. So I'm not sure the wording is good, but is what we meant by interface between classical and quantum information. And I will stop here. Effective theories for quantum many-body states, the idea that describing quantum many-body states is still a challenge so difficult that what we need is effective theory. Although in principle, a universal quantum computer could describe many-body problem, but this is a personal comment. Okay, go ahead.
Well, okay. So before going through this list again, I want to stress what Ola already said. I think what came out in the beginning was that basic science is the place to foster the exchange, the training, and also the networking within Europe. And that's sort of the particular role that we see here for young people, but also for senior people to exchange between countries. That's what is usually not funded by national funding agencies and not funded by ERC, which is funding individuals, basically. Yeah. And so we thought as a boundary condition for calls, so that would be the best format actually here in basic science.
Yes, what we have in mind is the former program of human capital and mobility. Exactly. You remember that?
So some of us remember exactly these programs.
And it's a program, yes, it's a program to foster collaboration and at all the levels, including the level of professor on sabbatical years and things like that.
And we shouldn't see that it does not need to be a huge system. Well, if there are 10 nations, fine, but 3 is not bad, okay? There should be flexibility in that.
And it also should include, of course, and that's why we write it down here, engineers and potentially, even if interest is there, people from industry. So let's come back to the list. This is not a complete list, yeah, it's just some ideas. One topic was new cooling techniques for species that cannot be cooled, including complex molecules and so on, fundamental limits of quantum sensing. That is, of course, in the sensing session as well, but ultimate control beyond the single particle level, also in chemistry, might be a topic. And then we had a little bit of a discussion about gravity effects, quantum tests of gravity. But this is just an incomplete list of things.
Etc.
Etc. Exactly. So that is our one single slide.
So the main message is this one. This is what we have.
So we thought this is what should be included in these coming calls, that it should be collaborative, cross-disciplinary change and training program.
Okay, we continue with the last two, the cross-sections. So I just see Anouk, you want to continue? Theory and Tony? What's happening here? Nothing's happening here? Oh.
Okay, so I must say I'm impressed about all the discussion that was happening in the other groups. In my group, we just mostly focused on a single point, which is what I try to tell you about. So, I mean, what is clear is that during these years, the role of theory has changed. So if you compare the two figures that Tommaso was, for instance, showing during his presentation, so at some point it was a vertical pillar at the same level as the others, and then it became, it was somehow split between two pillars, one cross-cut pillar, the software and theory, which is the one I'm representing, and the one on basic science. And actually, for instance, when I was preparing the contents for our session, I had to look at what the documents, the strategic research agenda says about software and theory. And there is no section on that. So I had to go to all the vertical pillars and pick up the sentences from all the vertical pillars about software and theory. And I think the situation is not ideal, I would say. It's not clear. So even when I was here, there were theorists, colleagues, that were coming to me and they were asking me, should I go to the basic science session or the software and theory session? Okay, so this is this sort of dichotomy. It would be nice to fix that. So perhaps I would say that a possibility is like we have something that we call software or something like that, which means theoretical work that might be of interest to industry. And then something where the industrial application is less clear, where that goes into basic science. So I will talk about this potentially theoretical work of interest to industries. And I think we should think, well, this shouldn't go to basic science. And we can think of whether we should give more visibility to this type of work. And this is what I want to present with you. Okay, this is the topic of discussion. We didn't reach any agreement, but this was the main message. Okay, so is it time to have a sort of vertical pillar on quantum software? Okay, so it will play with the same rules as the other vertical pillars. So you need industries for that. So this removes a lot of theory from the picture. But you can think of quantum algorithms, machine learning, methods for verification. Well, you see it there. Okay. And I must say that I was involved in several projects for the first column, and I detected more interest from industries on some theoretical work. So maybe it's time for that. So what are the possible advantages? I think it is clear that there will be a quantum software industry at some point. Okay, so the question is whether we want to make it visible now. So I think it's also a situation where it's easier for Europe to play a leading role compared to others. Okay, but at least we have chances to have a leading role. So also someone mentioned, I think it's clear, it's easier for startups, perhaps started there. And also, I think we should think about it whether it is convenient to start this discussion now. Okay, I think that some of the ingredients. I mean, if I want to submit a project with industries on algorithms, I can do it with the present startup. Okay. In fact, in the previous call, there was a project on quantum algorithms that was submitted, or several that were submitted to quantum computational. So I'm not saying that this research is not covered by the person structure. I'm saying whether we should make it more visible and strategically transparent. So I'm thinking, for instance, of an industry who is interested in software. This industry will have to go through the same process I was telling you. So we will have to go to the agenda and look at the vertical pillars and look at what they say there about software. Well, maybe if we have something clear, it simplifies their lives. Of course, there is a risk for that. If we make this transition to something like this now, it may become empty because maybe, I don't know whether there is critical mass or not. So maybe also it would be nice to start actions to get in whether there is interest from industries.
And the last one, engineering and control. You go ahead.
It's in there.
Okay, 2 slides between you and lunch, or me and lunch. Okay, very brief wrap-up of our session. We had a very mixed audience, and I was happy to see with participants from theory, experiment, and industry and academia. There was a brief introduction into quantum optimal control and the present state of the art with respect to its practice. And one of the open questions there, which I think is very relevant in the near future, is how to quantify what we want. What are the right figures of merit? And that I think has not yet been answered completely. And followed by a presentation of the present challenges for quantum engineering, both in terms of tasks and obstacles. There was the question, or quite long discussion about connection between science and industry, and how to view the engineering challenges from a component/device/systems point of view. So that was just a brief wrap-up of the discussion, and these are now the points that we wanted to stress here in the plenum. And that is one input that was made, I think, in particular, became clear in the discussion that there is quite a difference in when people speak about engineering, what they mean. So it can be engineering of tools, and it can be engineering of final products, and these are 2 different issues, and that should be differentiated, and they come with different problems.
Then we had a topic on openness of hardware versus IPR. So openness of making it widespread as possible and cheap as possible versus allowing companies to earn something. Definitely a topic to discuss more. And in connection to that, also trust and verification in the components. So how do we ensure everything works as it's supposed to work?
Okay, the industry participants of this session stressed the importance of motivators and also that it's important to keep the end user perspective in mind, which I think is a bit challenging given the fact that the engineering and control session is defined as a horizontal platform and not one of the pillars. But okay, that was the opinion in the discussion.
If you do also the next one, because I think that's control side more.
Okay, and then this is a really important point, maybe one of the central parts of the discussion is what is the role of the challenges and have they been defined yet? And I think they have not yet completely been defined. So one task maybe of the coordination action or of meetings like this is to extract common engineering and control challenges from the vertical pillars.
And a longer discussion was also on how do we actually make the connections happen between industry and academia, and possibly organizations in between, like the RTOs, Fraunhofers, and so on. And so because the application systems engineers sit in industry, but somehow we need to bind in the new developments from the academia. And so workshops was discussed as a possible topic there, or possible way forward, but hopefully there will be more.
Okay, now I'm coming back to the what could be common goals, or how do we find them, how do we define them? And one option is to put the cross-cutting themes, to extract them from the research projects which will be funded in the first round of the flagship. I think that could be a first iteration and then substantiated by, for example, a community consultation.
Yes, and finally we had to push, we definitely need some standardization between of the interfaces, so for the hardware to match, hardware, software to match, have as many as possible off-the-shelf parts to make this really worthwhile, that we get one platform out of it, not many different parts.
Thank you.
Yeah.
Thanks for your patience, and we'll continue with lunch, and then we'll continue at 11:50, so 5 minutes after schedule, to give you a little. 12:50, of course. 11:50 would be impossible.